Welcome to this video on Einstein coefficients. Einstein coefficients are meant to describe the rates of absorbing and re-emitting of photons by atoms. So for example, we might have an atom here with a nucleus and an electron going around it, and by absorbing a photon, it can jump into a higher energy state, where the energy of that photon is now stored inside the orbital of the electron around the nucleus. And then after some amount of time, this excited atom with an electron in the excited energy state can transition back into a lower energy state, and as it does so, re-emit a photon with the corresponding energy difference. So Einstein coefficients were designed to describe the rates with which these atoms absorb and re-emit photons. And an important point here is that these Einstein coefficients are macroscopic approximations, which means they don't describe what happens on an individual atom or molecule basis. They describe macroscopically what happens on average to a whole collection of these atoms or molecules. Under the hood, what's actually happening when we absorb a photon into an atom or a molecule is a quantum mechanical process that we can only calculate explicitly for very simple systems, for example, a single hydrogen atom. And even in cases where we can calculate explicitly the quantum mechanical processes of absorbing and re-emitting photons, there's still an inherent randomness to this process, which is why I say that this is a stochastic quantum mechanical process. So on an individual basis for a single atom, for example, we can't know precisely when it will absorb a photon and when it will re-emit a photon. However, when we get whole ensembles of these atoms together, then we're much more able to make statements about what happens on average and what the rates on average for a whole collection of atoms would be. So the first process we'll talk about, which will be described by an Einstein coefficient, is spontaneous emission. And this describes the case where we have an atom in an excited state dropping into a lower energy state and releasing a photon. And just to be concrete, we're going to pretend that this atom only has two energy levels, and I'll call this outer one energy level 2 and this inner level energy level 1. And because we need to describe a whole ensemble, I'm going to talk about the number of atoms in the 2 state. And technically I'm going to use this to mean number density, which is the number of atoms per centimeter cubed in the excited state. And then some of these atoms, when they're in the excited state, state number 2, drop into the first energy state, which I'll describe as N1, which is the number of atoms per centimeter cubed in the lower energy state. So we're turning atoms in the 2 state into atoms that are in the 1 state, and in doing so, release a photon whose energy, h nu, is equal to the energy difference between state 2 and state 1 in the atom. Now, universally, regardless of the atoms or molecules that you're experimenting with, if you start these atoms and molecules uniformly in an excited state and graph how many of them remain in that excited state as a function of time, so here we're graphing N2 as a function of time, starting with some fixed value at t equals 0, universally, we see a decay law that proceeds exponentially. We see that the number that remain in that state is proportional to e to the minus t over tau, where t is the amount of time that's elapsed, and tau is a time constant that seems to be, to the best that we can measure it, intrinsic to the transition. If I choose a different transition, a different atom or a different molecule, and talk about a different energy transition in that, it could have a different time constant. It still decays exponentially. So given that all electronic transitions seem to obey this exponential decay, the part of this that's going to be unique to this transition is this time constant here, which means that it's our first likely candidate for an Einstein coefficient. And in fact, we define the first Einstein coefficient to be the A coefficient, the Einstein coefficient for spontaneous emission between the energy state 2 to 1 is defined to be 1 over tau. It has units of inverse time, so seconds to the minus 1, and it controls how easily an atom drops down into the de-excited state. So if A is large, our exponential decay is steeper, which means it decays faster. Another way of saying that is it has a shorter half-life. And conversely, if A is small, then we decay less quickly. And I've defined this time constant here to be relative to an exponential e. Another common time constant that's used is the half-life, and that's just changing our base of our exponential from e to 2. So the half-life of an atom is just the natural log of 2 over A21. So that's spontaneous emission with its own Einstein coefficient, A21, the numbers indicating that it's dropping from the second energy state down to the first energy state. And this Einstein A coefficient has units of inverse time. It's measuring a rate at which atoms in the excited state drop down into atoms in the de-excited state. And I can use this Einstein A coefficient in all sorts of useful equations. For example, the rate of change of my number of atoms in the ground state, the N1 state, with respect to time at any instant is going to be equal to, in the absence of any other processes going on, just considering spontaneous emission, will be the number that are in the excited state times A21. And of course, this also governs how many are in the excited state. The rate of change of the number density of atoms in the excited state with respect to time is equal to minus N2 times A21, because every emission process moves one of our atoms from n equals 2 state to the n equals 1 state, and therefore robs the n equal 2 state of one of the atoms. And in fact, it's this equation right here, this differential equation, that gives us this solution that the number density of atoms in the excited state as a function of time, in order for the time derivative of it to be proportional to itself, we naturally have an exponential solution. So that's spontaneous emission. Next, we're going to talk about absorption. Absorption kind of looks like the reverse of spontaneous emission, although we're going to find out that it's not exactly the reverse process. We begin with an atom in the first energy state, we end up with an atom in the second energy state, and it was the absorption of a photon that triggered the change in state. So for spontaneous emission, we had the Einstein A coefficient, which was a rate. And we'd like to calculate something analogous for the absorption case. We'd like to have an absorption rate. Now you might think that we should just invent a new Einstein coefficient, that is the rate for absorption. But it turns out that would not be intrinsic to the transition, because we have something external to the transition that absorption rates depend on, which is this photon right here. If we have more photons, we'd expect our absorption rate to go up. So let's posit that the absorption rate should be proportional to the intensity of the incoming light, if that light has the correct energy to cause a transition. Then, given a certain intensity of photons, we can invent a coefficient that governs the probability, given a photon, that we make this transition. And that could be something intrinsic to this transition. And we will call that a B12 coefficient. So an Einstein B coefficient means that we are involving a photon. It multiplies a specific intensity, and it takes us from the 1 energy state into the 2 energy state. So that's what B12 means. Now this is getting a little ahead of ourselves, but just to make sure that we're technically correct here, this intensity that we plug in here, what we actually mean is not just the intensity in one particular direction, which is what I sub nu is usually meant to indicate. We actually mean the intensity from any direction. So we'll average over all 4 pi steradians our intensity in that direction, integrated over solid angle. And it turns out that in order to absorb a photon, we need its energy to be approximately the energy difference between these 2 energy states in the atom, but it doesn't have to be exactly, perfectly the exact right energy. If you're slightly off, the atom can absorb the photon and sometimes get the difference in energy from somewhere else, either from the quantum mechanical uncertainty in the energy of your photon or from the motion of the atom with respect to the photon. And the thing that governs the width in frequency that the photon absorption of this atom can have is called the line profile function. And so we actually also integrate this against the width of this transition in frequency. So this is a line profile function. And we integrate this over frequency. And I should mention that line profile functions have units of inverse bandwidth. So when you integrate them over frequency, they integrate to 1. And so fundamentally, the units of this construction here are the same units of specific intensity. And it's just measuring the number of photons coming from any direction over any frequency which can be absorbed by this transition as determined by the line profile function of this transition. So anyway, as I said, this is just a detail. Fundamentally, our Einstein B coefficient is something that takes the number of viable photons for causing this transition and multiplies that to give us a rate at which these transitions from the n equals 1 to the n equals 2 state will happen in this atom or molecule. Now the units of specific intensity are ergs per second per hertz per centimeter squared per steradian. And we know that the units of rate are going to come out to be inverse seconds, which tells us that this Einstein B coefficient is going to have some funny units. Its units are going to be hertz times centimeter squared times steradian over ergs. But critically, it doesn't have the seconds in there, so that when we multiply these two, it leaves a seconds in the denominator. So these are the units of an Einstein B coefficient. And I'll tell you right now, I don't memorize what the units of these Einstein B coefficients are. I just know that when I multiply them by a specific intensity, I need to come out with a rate at which a transition happens. So just to simplify my notation later, I'm going to define this quantity here, the integral of the specific intensity around all angles and over the bandwidth of the transition. I'm going to call this a new letter, J bar, the bar kind of meaning an average and J being something like a specific intensity. So let me go ahead and erase I new from over here and put in a J bar, where we understand that J bar still has the units of specific intensity. So now, with my Einstein B coefficient, I can say, for example, that the change in the number density of atoms in the excited state with respect to time is equal to however many are in the ground state, N1, times B12, which is my Einstein coefficient, times however many photons are available for causing this transition, which is J bar. And similarly, just like above, these get robbed from the atoms that are in the ground energy state. So the change in the number density of atoms in the ground state with respect to time is going to be just the opposite. It'll be minus N1 B12 J bar. This equation looks a lot like the equation governing spontaneous emission up here, which will tell us that in the absence of any other processes like spontaneous emission, if we start with a bunch of atoms in the ground state and shine some light on it, we will see an exponential curve decaying, where we will see fewer and fewer atoms in the ground state as they all migrate into the excited energy state. Now I'm going to consolidate things here a little bit so that we can talk a little bit more about this balance of absorption with the spontaneous emission that we covered already. So we had spontaneous emission with an Einstein A coefficient, A21, and we had an absorption coefficient, B12, which took atoms from the ground state and put them into the excited state. Now we've said before that these Einstein coefficients we are taking to be intrinsic to the transition. So these are both intrinsic properties of a transition. So we pick a transition and it has an inherent stability after which it will spontaneously decay and emit a photon, and it has an intrinsic absorptivity where given a photon, there's a certain probability that we can absorb that photon and move into the excited state. Now, if these are intrinsic properties, then they need to work out in any situation that we find atoms in, including in thermal equilibrium. So suppose we are in thermal equilibrium. Now, I'm not saying that Einstein A and B coefficients depend on thermal equilibrium. I'm just saying that they are intrinsic properties of transitions. Sometimes we are in thermal equilibrium. Let's just find out what that means for these Einstein A and Einstein B coefficients. Well, we know in thermal equilibrium that the ratio of the excited state to the de-excited state in an atom is given by Boltzmann statistics, which says that the number density in the excited state over the number density in the ground state is equal to the degeneracies of those states, how many microscopic states correspond to a macroscopic energy state, times e to the minus E2 minus E1, so that's the energy difference between the states, over kT. So those are just Boltzmann statistics. Now in thermal equilibrium, rates need to balance, which means that the number of atoms entering the excited energy state needs to match the number of atoms leaving the excited energy state. So the number leaving the excited energy state is however many we have in the excited energy state times the Einstein A coefficient for spontaneous decay. And this rate needs to match the rate for entering that state, which we've described before with absorption being N1 times J bar times B12. Now I'm just going to leave that there for a second. I'm going to add one more thing. Suppose we are in local thermodynamic equilibrium. Now, local thermodynamic equilibrium is just a little more stringent than thermal equilibrium. It means that our radiation field is also in equilibrium with the ratios of states here, which means we can actually know in local thermodynamic equilibrium what J bar is. The radiation field becomes Planckian, which means that J bar, the intensity, is given by the Planck function, B nu, which is equal to 2h nu cubed over c squared times 1 over e to the h nu over kt minus 1. Okay, so we've started with a bunch of atoms and some photons, and then we've decided that we would write down the conditions of local thermodynamic equilibrium in terms of these Einstein A coefficients that we've invented and have said are intrinsic properties of these transitions. So now, given this rate balance equation here and these conditions of thermodynamic equilibrium, the Boltzmann statistics, which are governing the ratios of the states of the atom, and the fact that in local thermodynamic equilibrium, the radiation field has to be given by the Planck function, we can do something interesting. If I divide the N1 onto the N2 side so that I have N2 over N1, which I can replace with the Boltzmann condition, I have that G2 over G1, e to the minus E2 minus E1 over KT times A21 over B12 is equal to, and now I have J bar on this side. I'm going to replace J bar with the Planck function because we're solving this for local thermodynamic equilibrium, which means that this needs to be 2h nu cubed over c squared times 1 over e to the h nu over kt minus 1. So this balancing was something that Albert Einstein, in fact, worked on doing in the early 1900s. And he got to this point, and something interesting happened. He looked at this section right here. That's a clear exponential. And if you set h nu to be the energy difference between E2 and E1, so saying that h nu is equal to E2 minus E1, he looked at this exponential in the denominator, and these are basically the same thing. But there's one problem here. There's a minus 1 in the denominator of the Planck function that comes from photons being bosons. So this is just Bosian statistics. And the problem is, for A and B being intrinsic properties of a transition, there is no way for the ratio of them to somehow give us a minus 1 in the denominator like this. These functional forms are not compatible, which is to say there's no universal solution for A and B that would be intrinsic to the atom that could also reproduce this minus 1 in the Bosian statistics, which is really only important when you're at low temperatures. Now, a normal person, when faced with this, might have suspected that maybe we've made an error in the assumption that A and B are intrinsic to the atoms, and maybe we would change our assumptions and try to solve for something where A and B were somehow dependent on temperature or something. But that is not what Albert Einstein did. Albert Einstein saw that these functional forms were not compatible and drew a very interesting conclusion. He noted that these functional forms could become compatible if he introduced one new term. He saw this and said, this means that there must be a B21, which, as I've said, is a rather bold and, for me, not at all intuitive conclusion to draw from this mismatch in the functional forms here. But it turns out, as with so many other things, Albert Einstein was correct. So what is the stimulated emission that Albert Einstein hypothesized? Well, in some ways, it's the true opposite of absorption. Before, we had kind of thought that spontaneous emission and absorption were opposites because one absorbs a photon, the other one produces a photon. But it turns out the true opposite of absorption is stimulated emission, where we have an atom in the excited state. A photon of the energy required to cause the transition from the 1 to 2 state here comes by, and the presence of that photon helps the atom drop into the de-excited state, where now we have both the original photon that helped cause the transition and an additional photon related to the energy difference of the transition in the electronic states that just happened. Now, the idea that a photon of the right energy can help cause a transition to happen is a little bit strange, and for me, a bit counterintuitive. The way I've ultimately come to terms with this is to think of the different states that an electron could be in around an atom as these kinds of resonances, where you can imagine having a rope and you shake the rope a little bit. If you shake the rope at the right rate up and down, you can get a standing wave to appear on that rope. It's a kind of resonance, and you can get the energy of your shaking to be absorbed into that rope. And that's kind of what these photons are doing, is they are shaking these electrons at the right rate in order to get them to move into a different energy state. And so I think of stimulated emission as a photon coming in, and even though the electron is already in the excited state, it's shaking the rope at the right rate for causing that transition. And what that can sometimes do, just the fact that you're interfering with the atom at the kind of right resonant frequency, makes it possible to extract that energy back out of the system at that resonant frequency. So the presence of this photon shaking this electron at the right energy level that would help it go from 1 to 2 also can help extract that energy from the system and help the electron drop from 2 into 1 and create 2 photons instead of just 1. So that's my hand-wavy kind of intuitive picture of what stimulated emission looks like. Mathematically, it looks just like absorption. We have a rate, and that's a rate of going from the n equals 2 to the n equals 1 state. And that rate, simply the number of photons that are around that can cause that transition, which we know is J bar. And we have a coefficient B21 now, which is analogous to the B12 coefficient. It just works in the opposite direction, going from the n equals 2 to the n equals 1 state. So now we can correct this rate equation that we had up here. Einstein says this rate equation was incomplete because it did not account for stimulated emission. The true rate equation that corresponds to thermal equilibrium would be that the rate of spontaneous emission out of state 2 into state 1 is balanced by both the absorptions that land you from state 1 into state 2, but also those excitations, the absorptions, are balanced by the stimulated emission that's caused by the same photons, the same J bar, but they encourage atoms in the excited state to de-excite back down to the 1 state. And this is the true rate equation. So now we're going to do the same thing that we did before. We're going to use our Boltzmann distribution and our Planck distribution in local thermodynamic equilibrium. So we'll say, suppose we are in LTE, and this is exactly what Albert Einstein did. And I'll spare you a little bit of the algebra, but we can manipulate our rate equation to say that J bar is equal to N2A21 over N1B12 minus N2B21. And if I divide the top and bottom both by N2, this is also equal to A21 over N1 over N2 B12 minus B21. Now we'll plug in our Boltzmann distribution. And notice that we have N1 over N2 here, not N2 over N1, so we have to flip our Boltzmann distribution upside down. So it's G1 over G2 e to the positive delta energy over KT minus B21. And I'm going to go ahead and divide B12s on both sides out of both the numerator and the denominator. All right, now this is the thing that has replaced what was happening on this side of our equation in thermodynamic equilibrium, and this is something that needs to be equal to the Planck function, which is what we're replacing J bar with in local thermodynamic equilibrium. And now here we finally have something that has the correct functional form. And this can be solved for intrinsic properties A21, B12, and B21 with the following equations. If G1 times B12 is equal to G2 times B21, and if A21 is equal to 2h nu cubed over c squared times B21, then these equations will be perfectly equal in local thermodynamic equilibrium. So let me box that up here. These two equations are called the Einstein relations, and they are fundamental relationships between the Einstein A and Einstein B coefficients that exist for any transition in atoms and molecules that involve absorbing and emitting photons. And even though we use local thermodynamic equilibrium to derive them, the idea was that these were intrinsic properties of the transitions, that these Einstein relations hold no matter what. They were just required to have this relationship in order to reproduce local thermodynamic equilibrium with its associated Boltzmann statistics for the ratios of the excited and de-excited states, and the Planck function being the radiation field in the background. And what they really say, because these are intrinsic and we can relate the B21s to the A21s and the B12s to the B21s, they say that there is only one number that you actually need to describe everything that you need to know about a absorption, stimulated emission, or spontaneous emission process in an atom, and that is the A21 coefficient. From that, you can calculate what the B21 should be, and you can calculate what the B12 should be. So the inherent strength of a transition is governed by one number. It's the A21. If you have a high A21, you have a high B21 and B12, which means that you very easily absorb and re-emit photons. And it also means that you decay faster out of an excited state spontaneously. So strong transitions, ones in which you can absorb photons very easily, are also inherently less stable transitions. They can decay very quickly. And conversely, if you have a low A21, if you're fairly stable, you stay in the excited state when left there, also means that you do not interact with photons very strongly, and you have small B coefficients for absorbing photons and being stimulated to emit photons by them. And one last thing I'll mention here, this inherent strength being governed by an Einstein A coefficient, you'll sometimes see another thing called an oscillator strength, which is basically also measuring the strength of a transition in an atom or molecule. An oscillator strength is related to an Einstein A coefficient by 2 pi e squared, where e is the charge, over lambda squared c times the ratio of the degeneracies, and this F12, is the oscillator strength. So if you look up the strengths of transitions on a table on a NIST archive, for example, you may see A21s, the Einstein A coefficients, or you may see the oscillator strengths, F12s. They're fundamentally related. You just get the oscillator strengths by modeling the excitation of the electronic state as a damped harmonic oscillator. So that's basically everything you need to know about Einstein coefficients, which, just to review, are the fact that there are intrinsic rates to the transitions in atoms and molecules, and that those intrinsic rates or intrinsic strengths of these transitions can all boil down to a single number, the Einstein A coefficient governing spontaneous emission, and that there are Einstein relations that relate that Einstein A coefficient to the corresponding Einstein B coefficients that govern the absorption and emission of photons. In order to derive the Einstein relations, we assumed local thermodynamic equilibrium so that we could relate the ratios of states to the shape of the emission, J bar. But remember, these Einstein coefficients were intrinsic to an atom. It does not depend on whether the atom is in thermodynamic equilibrium or not. We just use the fact that because they are intrinsic, they also need to work when we assume local thermodynamic equilibrium. It has to produce the right answer. And using that, we found that there were fundamental relationships between these Einstein coefficients. They weren't independent numbers. Another important thing that we did was to write down a rate equation that used the Einstein coefficients to determine the rates at which atoms were entering and leaving the different states in a two-energy state atom. And later, not in this video, we'll explore how to actually estimate what an Einstein A coefficient should be, and we'll discuss detailed balance, which allows us to extrapolate from the simple two-energy state atom to atoms that have many different energy states. And we'll find that there's basically no change, that all of these equations still work. All right, so those are Einstein coefficients.